Just have to remember to copy that to my USB before we leave. Okay, so we're going to talk about cluster analysis. This is a method of unsupervised learning. And together with principal component analysis, it's a method that what it tries to do is tries to simplify our data in some sense. With principal component analysis, what we did was to reduce dimensionality. So we have p variables, and then with the cluster analysis, with the principal component analysis, we try to reduce that to a smaller number of variables that could represent most of the variability. Okay? This is another way that we can simplify data with cluster analysis. Remember, supervised learning is what we have seen so far. Essentially, we have a prediction to make. We have a bunch of predictors and then a response, whether that response could be categorical, which is the case that we saw for classification. And but we always have the predictors and the corresponding response. And eventually, what we want to do is, for a new set of predictors, we want to predict the response. In unsupervised learning, we don't have that response. In supervised learning, all we have are the equivalent of the p-predictors. That's what we have. So there is no response here to predict. And what we want to do in unsupervised learning is discover something interesting about these factors. In PCA, we wanted to reduce dimensionality. In cluster analysis, we want to see how the different values for the predictors group together the observations. Okay, so that's it's perhaps the most common example of unsupervised learning. Although PCA is often used, it's not used that nowadays that often because of the computing power. Before we needed to reduce dimension to do some things because of the limited computing power. We don't have that limitation now. So it's a common example of unsupervised learning. It is also known as data segmentation. That's in the data mining community. They know this thing as the data segmentation. And in machine learning, we know it as instead of data segmentation, which is the term that we use in data mining, we use it as class discovery, okay, or category discovery, group discovery. Because what we try to do is discover if the observations have groups that have certain things in common. So it's a bunch of algorithms and methods to organize a set of data in homogeneous subgroups called clusters. Now, there are many methods for clustering. We're going to see only two methods here, which are the most commonly used. This has applications in marketing. For example, we have a target population that we want to market our products to, but we don't know if certain products are going to be bought by a certain subgroup of that population. So we want to create subgroups of that population based on their purchasing characteristics, so that we can have a more focused marketing campaign. It's also used in biology to cluster cells according to their characteristics. When there is no knowledge about, for example, we saw an example here where essentially we're looking at the cells and see if the nucleus, there's some measurements that we took about the nucleus and so on, but they were classified previously. Here we do not know that. They're not classified, and we want to see if a group of cells have certain common characteristics. And in finance also, it is used to determine which, if there are companies that have some common characteristics that make them for example, more prone to break, to going bankruptcy, for example. And we don't know, we don't have enough history of how many companies have gone bankrupt, and we may want to cluster them according to their financial indicators. So there are many applications of clustering, a lot of applications in marketing. Okay? Now, both, as I mentioned earlier, PCA and clustering seek to simplify the data. In PCA, we want to find a lower dimension. And in clustering, we essentially want to group them in very few groups, maybe 2, 3, 4, 5 groups that we want to be able to cluster our data. We will look at two methods only, which are very common. K-means in hierarchical clustering. We'll start with the K-means method. And one of the something that's essential in clustering is to define what is our similarity measure. That is, if we have two objects, how we're going to classify them, how we're going to say that they are similar or they are not similar. So we need to define how we're going to measure similarity. For example, if we have that example of two variables, x and y, and if we define the measure of similarity as the Euclidean distance, then here we have two groups. Okay, we have two groups here, if the measure is Euclidean distance. But our measure of similarity could be a color. And if the measure of similarity is color, we have three groups, the reds, the blues, and the greens. Or we could have as a measure of similarity the form, the shape of the object. And this measure of similarity would lead us also to three groups, but these are different groups than these other three, because the measure of similarity determines how many groups we have of observations, okay? In image processing, the most common method of similarity is shapes and forms. We want to cluster images so that they look that they're very similar. Okay? Now, I took this example from a project that a student of mine made several years ago in practical. Okay. This is the first historical application that has been published of clustering. And that happened in the 1850s, and John Snow, an English physicist, plotted a graphical location of cholera deaths. And the locations helped identify where they were polluted or contaminated wells. So that's the first application of clustering, which is based on geographical distance, that was found in the literature. And that's an example of clustering. Clustering has been used also, for example, in Japan. They have been used to cluster areas with certain types of crimes occur. So they have, based on the analysis that they do of the types of crime, whether they are serious crimes like murder and stuff like that, or simple crimes like robbery, they do the clustering, and based on that they define their strategy for the police to, where they center the police and they focus the police in certain areas. Okay. Now, K-means clustering is the first algorithm we're going to see. We're going to illustrate this algorithm with simulated data. This is data that's simulated from two different populations. Now, one of the disadvantages that K-means has is that we need to pre-specify what is the number of clusters we have, which we don't know. We never know how many clusters we have, but that needs to be pre-specified. We'll see later that there's a way to determine which is the right number of clusters. or something that could be the right number of clusters. Now, because depending on K, we're going to get different clustering. Okay? If we define K equals to 2, we may get this clustering of this data. But if we say that K is equal to 3, we may get these 3 clusters with the K-means algorithm. And if K is equal to 4, we're going to get these 4 clusters. Okay? Now, what is the right value of K? We'll see the methods to do that. But initially, you need to specify some value of K. Now, how does it work? We're going to denote by C1 through C capital K the sets containing the indices of the observations in each cluster. Okay? So we have n observations, and each observation is going to be labeled from 1 through K, for K is the number of clusters that we have pre-specified. Now, the sets that we define here need to satisfy these properties, that the union of the sets is the whole space. Okay, we cover all the data with the different clusters. And the intersection of any of those 2 clusters is it's empty. There's an observation can only belong to one and only one cluster. Those are the 2 assumptions, the only 2 assumptions. Now, the idea behind K-means is that a good structure of clusters is one for which variation within the cluster is as small as possible. By variation, what do we mean by variation? Variation depends on the measure of similarity or dissimilarity. Okay? If we use the Euclidean distance, then variation would be the differences squared between each pairs of observations. Okay? So within the cluster, we want that the variation be minimum. If our criteria for similarity is shape, then the shape should be as similar as possible within the same cluster. And in parallel to the same, we would also want that units in different clusters be as different as possible. So I don't know if the notation here shifted for some reason. Variation within each cluster is a measure. Let me write this thing. I thought that, I'm not sure if in the PDF it's okay or not. So variation within each of the clusters is a measure, well, WCK. The W is because it's within, okay? It's within each cluster. That's a measure of how different the observations are from each other within the cluster. Okay? So if we want to assign the units to the K cluster, what we need to do is solve this problem. We need to minimize these deviations, these differences within each cluster. So we want to define the clusters in such a way that this sum of these variations within cluster is minimized. Okay? Now, as we mentioned that there are many ways to define variation within a cluster, and it depends on the similarity measure. We're going to be focusing here in this class in Euclidean distance. Now, we're going to define W of K, that is the variation within cluster K, lowercase k, as the sum of square deviations within that cluster. So we take all the observations in a cluster, and we subtract them, take every pair, subtract the 2 observations, square them, and add them all, and then divide by the size of the cluster. So this is the modulus of the cluster, which is the size of the cluster, the number of observations we have in that cluster. So we need to do that within each of the clusters. Okay? So CK, which looks like the absolute value is the modulus of CK, is the number of observations in the K cluster. Now, the problem to be solved then would be to minimize over all possible combinations of the observations, accommodating them in the K clusters, minimize the sum. So that's a difficult problem, because we would need to do all possible assignments of observations to the K clusters and see which is the arrangement or structure of clusters that minimizes the sum. So that's a very difficult problem to solve. And instead of solving that problem, there's an algorithm that was developed that has proven to be very good. I mean, trying to approach the actual minimum here, although what we're going to get is a local minimum. We're not going to find a global minimum. This is to find a global minimum, that's a very tough problem. Very tough in terms of that will be a huge computing effort, because we have millions of observations in one, like millions of customers, and we want to cluster them, and for each customer we have several measurements in terms of their characteristics, demographic characteristics, transactional characteristics, and so on. That would be very difficult to do. And so that we use an algorithm that at least gets us to a local minimum. And that's the K-means algorithm. The K-means algorithm is very simple. You have n observations, okay? So you take your n observations, and then at random, we assign numbers 1 through k to each of the observations in the data set. So we assign at random each a number. So we label them from 1 through k. Then, the first time we do the same, we're randomly assigning the numbers from 1 to k. Then we take all the ones that were labeled with number 1, we calculate the center of mass. We calculate the mean of all the ones that were labeled as 1. Then we calculate the mean of all the observations we labeled as 2, and so on. So for each, and that we do that for each of the K clusters. Now we have K clusters, which the first time that we have these K clusters, they have random the random selection of observations we made initially, okay? And we calculate the centroid, that is the vector of p-means of the observations in the Kth cluster. So we took all the ones, compute the average. All the 2's, and compute the average. Now the average is a vector that has the mean of the p variables. Then what we do is go back and check distances from all the observations to the center of each of these clusters, the initial cluster. So we calculate the distance of every observation to the cluster. And then we assign them to the centroid that's closest. Okay? So we check all the differences with the mean, and then we assign them to the one that's closest. Mean that the center of mass that's closest. And then we recompute the centroids for the newly formed clusters. Okay? Once I reassign them to a different cluster based on the distance to the mean, I have new clusters. And then I recompute the centroids. And I keep iterating until I don't have changes in the clusters. So this keeps going until there's no observation that changes that I have to move from one cluster to the other. Okay, is the idea of the algorithm clear?
Yes.
Okay. So this algorithm has the characteristic that the value of the objective function, that is the function we want to minimize, the value of that function gets smaller and smaller at every step. And that's clear from this expression, because if you look at the sum of the xij minus xi prime j prime square, we can write this thing down as 2 times this double sum, where X bar is the center of the clusters, right? X bar to Kj would be the center for the kth cluster. So as soon as we could, since we're starting them, we assign the observations to those cluster centers that are closest to the observation, we keep reducing that variability because we're assigning them to a place where they are closest to the mean. Now, if you look at what we did here, we assign a number from 1 through k to each observation, but that's a random number. We assign it at random. So the clustering that we end up with will depend on the initial assignment. So if I choose a different initial assignment, I'm going to get a different clustering solution at the end. So and that's because we are doing this assignment at random. Okay. So what we do to try to cope with that situation is we usually run the algorithm several times. We don't run it only one time. We run it several times with different random configurations, and then select the best alternative. The best alternative in terms of what? The alternative that gives us the lowest value for the within cluster variation. It's an example with simulated data that we saw in the slide 4. That's with 3 clusters, with k equals to 3. See, this is the data before we do any assignment. In the first step, I randomly assign them to a cluster. So at random, this observation ends up like a cluster, like a pink cluster, or purple, whatever that is. This one is starting as a yellow, and so on. After this step, then we recompute the means, the center of mass for each. So I take all the yellows here, compute its mean. And the mean for the yellows turned out to be here. Okay. Then I take all the greens, compute the mean, and the mean for the greens turns out to be right here. Okay. I can barely see the green here. And then I do the same thing for the greens one, right? The greens and the yellows. The yellows and the pinks, right? I'm going to call it pink, although it's not really pink. But I compute the center of masses for the 3 different clusters that we've defined. Once I do that, I recolor and reassign the observations according to which is the center of mass that's closest to the observation. So on the iteration 1 of step 2b, what I do is I assign this to cluster yellow because these are closest to this yellow mark than the other observations. They are closer to yellow than to the purple, for example, or to the green. So I reassign them according to which center of mass is the closest. Once we do that, then we recompute the center of masses. We recompute the center of masses, and now my center of mass for the yellow ones is here. Center of mass for the purples is here, and the center of mass for the greens are here. It's here, it's right here. So I have new centers. Since I have new centers, I reassign the observations now. I recompute distances from all observations to different center of masses and assign them according to the one that's closest. So as you can see from here, from this step to this step, which was changed? See, from this step to this step, here to here, this one was originally, this area was yellow, and now it's, I'm sorry, this is not the one that changed. I picked the wrong one. It be one that changed. Then this is this one was yellow. When I check the distances to different to the centers of mass, that is reclassified now as green. And this one that was yellow is also moved to be green. Okay? So those are two that change. There may be others from there that also change. Around here, for example, look at these ones here. We change now, they're green. Okay. And then the procedure would follow, we recompute the, once we do this thing, we recompute the cluster means and reassign the observations. And the algorithm stops when there's no change, when I do not have to move an observation from one cluster to another. That's how it works. And then one of these keyboard here. Now, with the same observations that we simulated, in k is equal to 3, if we use a different number of random assignment at the beginning, these will be the n configurations for different random assignments, initial random assignments. So that's why we do this thing several times, because every time we do it, we get a different configuration for the clusters at the end. And then we compute, this is the within cluster sum of squares, or within cluster variation, let's call it like that. And then we select the one that gives us the smallest within cluster variation, which would be either this, or this, either one of these four, okay? Would be the selected one. Because that's where we obtain the smallest within cluster variation. Okay, are we okay so far?
Yes.
Yes.
Okay, let's look at this simulation of how this works. It's almost like it's the same thing, except that this algorithm that I have here, instead of assigning at random the numbers 1 through k, what it does, it starts with centers, cluster centers at random. Okay? That's the only difference, but the procedure is exactly the same. So I'm going to go here, and I'll choose the centroids. Okay, I can do this. I'll choose the centroids, so I can choose them randomly, or I can choose the farthest points as centroids. So I'll choose the centroids, and I'm going to use this Gaussian mixture data. We have three, this is data simulated from 3 normal distributions, 3 bivariate normal distributions. Now, I said I'm going to choose the centroids. I don't know if in this case, where we only have 2 variables, graphically we can try to at least intuitively say, okay, there seems to be 3 clusters, right? In this case, if we're looking at the picture, it's going to be clear that we have 3 clusters. Normally, we are working with data, with high-dimensional data, where we cannot see graphically how many clusters are intuitively right? So, since I'm not seeing anything, I'm going to say that there's 4 clusters. I'm going to say 4. Then I said I'm going to pick the centers myself. So I'll say 3, and then we'll change it to 4. I know, because I'm looking at data, that I should have centered the 1 point here, 1 point here, 1 point here. But this is just to show that the algorithm will converge with this type of separation. When I can have this type of separation, which is a sort of a linear separation, let's say, between the clusters, this algorithm works fine. So I'm gonna start the algorithm. So I assign this thing, this cluster means. Then based on these means, I assign those observations to the center that's closest to the observations. So all of these are called as red. These are blue and these are green because these are closest to the red one, these are closest to the green one, and these are closest to the blue one. Okay? Now I updated centroids, so that's the first step. Right? Now I have my initial assignment. This is the equivalent thing that we mentioned as numbering or labeling the observations from 1 through 3. So all of these were number 1, all of these were number 2, and number 3. Now I update the centroids because I need to consider all the reds and compute the centroid now, and all the blues and all the greens. Update the centroids. When I update the centroids, these two clusters pull that red center to this area here. Now once we update the centroids, we will reassign the points according to which is the centroid that's closest. So you update the points, you assign the points. And once I do the reassignment, I update the centroids. Then I reassign the points, update the centroids, and I keep doing this thing until I don't have any change. Here still is changing, you see? I'm still changing there. That's still changing. That's still changing. So I need to, when I stop when these things stops changing. Okay? Of the centroids, and it's not changing anymore. So it converts to this thing, and it will tell me that these are the 3 clusters. Now, since I don't know actually how many clusters are there, I will go with these decisions, but that's where it converts, right? Because I don't see any more changes. Now I have assigned the points at random, which is the actual algorithm, that's what it does. It does the assignment at random. So I'll do the assignment, and I'll use the same data at centroid, and it adds them as at random. And I go with the algorithm and do the same thing, update centroids, reassign points, update, reassign, update, reassign, update, reassign, and there's no change. So I finish here. Okay. So that's why we have to repeat the procedure many times to make sure if we were to compute the variability within each of these clusters, that variability will be smaller than in the previous one that we did. And we would choose the one that gives us the smallest value. Okay? I'll do a random assignment again, and I'll do the same. And that should, let me go randomly, and I'll do the smiley place. This is a case where this method is not gonna give us anything close to what the actual clusters are. Because here it's clear that I have 1, 2, 3, and 4 clusters. Okay? That's the 4 clusters. I have 4 clusters. But there's no way this algorithm is going to get to that because there's no way to linearly separate the clusters. So the algorithm will never get close to this thing. It will get something. I add that centroid. I'm going to say that it's 4 clusters. I'm going to add another one, 3, and I add 4 clusters. And I go add centroid. I'm sorry. I added 5 clusters. I'm going to restart this thing randomly to have only 4 clusters. 1, 2, 3, 4. Now I go and I start updating the centroids, reassigning the points, updating, reassigning, updating, reassigning, until I have no changes. And once changes stop, once I stop reassigning data, that's when the algorithm stops. Okay? It stopped there. There was no change now, so it will stop. That will be the 4 clusters that the algorithm finds. Okay? Okay. So that's the algorithm. Now, we'll see that there are methods to determine how many clusters should we have. To determine the number of clusters, there have been several methods developed. There's no true answer. Let's say there's no unique answer. But there are 3 methods that are very common. And those are the 3 that we're going to see here. Ideally, we will choose the number of clusters where we get majority of votes of these 3 methods. Okay. Ideally, we will do the 3 and then choose the one that gives us that has a majority. Okay. So for the k-means algorithm, actually these methods can also be used for other algorithms, like the hierarchical method that we're going to see later. Okay? It's commonly used with the k-means.
Método La Pina está cabroncísimo, o sea, la neta.
Pardon me? I guess it was not for us, right? Somebody who's paying attention to that. Okay, so there are more than 30 methods that have been published to identify the number of clusters. And so there's no common agreement on which is the best method. But these are the 3 most common methods. One is to optimize the within cluster sum of squares. We're talking about the Euclidean distance here. Optimize the sum, minimize the sum of squares within cluster. And that's also called the elbow method. The average silhouette method, and the gap statistic method. So those are the 3 methods we're going to see. We're going to illustrate the 3 methods with simulated data from a bivariate distribution. Okay? We'll simulate data from a bivariate distribution, which is a normal with mean 3, standard deviation 1, and a normal with mean -4 and standard deviation 1. Okay? It's 11, so let's take a break here. Let's take a 10-minute break. Yeah, 15-minute break. A 15-minute break here. And let me stop sharing and pause recording. Okay, we're going to see these 3 methods then to determine the number of clusters. The elbow method, if you're going to see the charts, they look very similar to what we did in principal component analysis. Again, these methods can be used with any clustering method, but they're commonly used with the k-means algorithm because we need to pre-specify k. The elbow method, what it does, it analyzes the within sum of squares within cluster sum of squares, which we'll call WSS, although it could be WCSS because it's within cluster sum of squares, or simply within sum squares. The within sum squares is a function of k, the number of clusters. So essentially what we do is we run the k-means algorithm for different values of k. For example, from k equals to 2 through capital K, from 10, for example. And then for each value of k, we compute the within cluster sum squares, and we do a plot like the script plot that we saw in principal component analysis, the same type of plot. And we choose we look at where's the approximate inflection point for the graph, and that's what we consider as an indicator of the right number of clusters. That is, when increasing the number of clusters does not reduce significantly the within cluster sum of squares, that's where we stop. This is how it looks. It's we plot the total within some squares, within cluster some squares, and we plot it for, this is 1 cluster, 2 clusters, 3 clusters, and so on, and up to 10. And this looks like a good place to stop, 2 clusters. So this, because that's, if you look at here, from 1 to 2 clusters, there's a very large reduction in within cluster sum of squares. However, the reduction from the 2 to 3 is marginal now. Okay, it's marginal. So this is like the elbow. So this point will be the elbow of an arm. So we will stop at that k equals to 2. That's it. That's a simple method. Now, the average silhouette method. This method a little bit more, has a little bit more to it than the elbow method. But as I said earlier, it's useful to look at the 3 methods that we're studying here. The average silhouette method, what it does, it tries to measure the average quality of the clusters. So it's trying to measure how well each observation lies within its own cluster. Okay, that's what how do we define the quality of the cluster. Now, it is based on the fact that observations within a cluster are as similar as possible, and observations in different clusters are different as possible. That's the assumption. Which characteristics are evaluated in this method? One of the characteristics is what we call compactness or cohesion of the cluster. Okay. How compact the cluster is, in a sense that how close the observations within a cluster are among themselves. Okay. They're very close now. For example, a low within cluster sum squares is an indication of compactness, of good compactness, if it's very low. That's one of the characteristics. The other one is separation. How well separated is one cluster with respect to the other clusters? Okay, the larger the separation between the clusters, the more clear it is that we have the right clusters, say defined. And here we use 2 indices. One is the distance between cluster centers. So remember, each cluster has its center, its centroid, and we measure the distance between the different centers, and the minimal distance between pairs of observations in different clusters. So we want large differences between the means, and we also, when we compute the difference between observations in one cluster with observations from another cluster, we want that the minimal distance of 2 observations from 2 different clusters, that be large. So one is the means, and the other one is that the minimal distance between 2 observations in 2 different clusters has to be large. And the third characteristic that measures is connectivity, and that measures essentially to what extent observations within a particular cluster actually belong to the cluster, in the sense that they are connected with other observations in the same cluster. So essentially, those are the 3 things that are measured. Connectivity in particular has a value between 0 and infinity. And the objective is to minimize that. So with the minimum size of connectivity, the more connected observations are within a cluster. So for each observation, how is this computed? For each observation I, we compute the silhouette width, what's called the silhouette width, in the following manner. We take each observation x, y. Then we calculate the average distance, the average dissimilarity, the average distance. Well, dissimilarity, it could be distance, right? If we're talking about Euclidean distance as similarity measure, the similarity measure is the Euclidean distance. So we look at the average dissimilarity between and we're going to call that A sub I, between xi and the rest of the observations in the cluster. So how different they are in terms of Euclidean distance, for example, when each observation with respect to the other observation in the cluster. We take the average of that dissimilarity and we call it A sub I. Okay? Then for each other cluster C, for which xi does not belong to C, that is for all the other clusters where xi doesn't belong to, we calculate the average similarity and we're going to call that D of xi, comma C of xi, of the observation that belongs in the cluster we mentioned, okay? So, but for the other clusters that do not have that observation, we compute the average dissimilarity between that observation and the observations in other clusters. And then we define the smallest of those distances, out the smallest of those dissimilarities, we define it as the minimum over C, over all the clusters, of this D distance between xi and C. So in essence, we're saying the distance between xi and C for a cluster that's not where xi belongs to is going to be, we're going to look at the minimum over all clusters, and we're going to call that B sub I. That's the minimum of the distances between xi and observations in other clusters over all possible clusters. And finally, we average the silhouette width of xi as bi minus ai divided by the maximum between ai and bi. Okay? Of course, we never do any of these things by hand because we have a lot of observations. So we don't do it just by hand, but this is how the algorithm works to compute the silhouette. And what's the interpretation of this? Observation with a large SI. SI then is going to be the average silhouette width. We're going to call that S sub I. And the large S sub I, which is close to 1, we think that if those represent observations that are well assigned, so they are assigned to the right cluster, in essence. If S sub I is close to 0, that means the observation is roughly right between two clusters, okay? It could be the edge of one or the two, but it's essentially between the two clusters. And observations for SI less than 0 are likely to be assigned to the wrong cluster. So if SI is less than 0, then that means that observation is very likely assigned to the wrong cluster. So that's the interpretation of S sub I. This is how the chart of the average silhouette width looks like. And again, we look at the average silhouette width with respect to the number of clusters. And with this method, we're going to choose the observation that we're generally going to see this pattern. It will increase, let's say it will increase, and then we'll start decreasing. In theory, we should choose the number of clusters where the silhouette width starts decreasing. The software, we're going to be using points that are it draws a dashed line where the criteria is made. There are some hypothesis tests that are done. We will not cover them because that's getting too much into the details of these algorithms. But we can do testing to see if the right number is 2 or 3. That can be. But graphically, if graphically it's clear, we don't have to worry about p-values or anything like that. And that graph will tell us which is the right number of clusters. And finally, the gap method, and again, we also do this thing. We do the elbow method, we do the silhouette method and the gap method, and we take majority vote. And if two of them agree and the closed variable number cluster is 2, then we'll go with 2. Unless there is knowledge, subject matter expert knowledge that says that there are more clusters. Okay? That happens, for example, in marketing. Usually the people who know the products that they're trying to market have a feeling of how many clusters there should be in the population for the different types of products. Because when they develop the products, they develop them with a market target in mind. Now the gap statistic, what it does, it compares the intra-cluster variation, the total intra-cluster variation. It compares this intra-cluster variation, the total intra-cluster variation, for different values of k, with their expected values under the null hypothesis of the reference distribution. Okay? The null hypothesis is that there is no clustering, that the data come from a multivariate uniform distribution. P-variate uniform distribution, that would be the null hypothesis. So it computes the total intra-cluster variation and compares that with the expected value of that for given the null distribution, that everything is at random. There's no actual distribution generating the data, but it's just the uniform distribution generates everything. Now, the estimated optimal number of clusters is the value that maximizes the gap statistic. That is the one that yields the largest value for the gap statistic. We'll see how it's computed, which means that the clustering structure is away from the random uniform distribution. See, the larger the gap statistic is, the more evidence we have that we are away from the multivariate uniform distribution. How does it work? We group the observations, varying the number of clusters from k equal to, from 1 to a k max, a max value of k. And we calculate the total intra-cluster variation, which we will call it WK, right? The total intra-cluster variation. Then we generate B sets of reference from a uniform distribution. Okay? So we use the data to help us generate B different sets, capital B different sets of reference from the uniform distribution. And then we group each of these reference data with varying number of clusters also. So the same number we use here is the same number we're going to use here. Okay? And then we calculate the total intra-cluster variation, which we're going to call WKB, because that's going to be the intra-cluster variation under the null distribution of the hypothesis of a null uniform distribution. Okay? So that's essentially, we play the role of that expected value. Then we calculate the gap statistic as the deviation of WK, of the observed WK, from its expected value, which is WKB. Remember, WKB is computed based on these data reference sets that we generate from a null distribution, and then we use that mean to estimate the expected value under the null hypothesis of a uniform multivariate distribution. And then we're going to measure the distance between how these observed WKs differ from the expected value. And we call the gap statistic as the log of WKB star minus the log of WK. Now it will take the average from 1 through B, from capital B. Remember, we generate B subsets from the reference distribution. Generate the B subsets and compute that difference and then we choose the number that's the smallest value of k, such that the gap statistic is within one standard deviation of the gap at k plus 1. So we will always compare what's the gap at k, and compare that with the gap at k plus 1, and if that's within one standard deviation, that's it, we'll select that value of k. It will be clear with the chart here. See, here is the chart. The chart provides here that this is one standard deviation. So that's the observed value of that's the gap statistic, and that's the difference between the observed value and the expected value, computed based on the B subsets, and that's the one standard deviation. So we will go, for example, from here to here, we see that this observation is outside one standard deviation of the next k, okay? So for k equal to 2, this one is outside this interval, okay? Whereas, for example, this one falls within the next interval, this one falls within the next interval, and so on. So the first observation, the smallest k for which the gap statistic falls outside the one standard deviation interval for the next value of k, that's the one. So we would select k is equal to 2 here. Okay? So these intervals are the one standard deviation, the gap plus one standard deviation minus one standard deviation, and we'll stop when we find a gap statistic that does not fall on within the one standard deviation of the next gap statistic, the confidence one standard deviation interval of the next gap statistic. Those are the three methods. Okay. Now we're going to do next is we're going to see how this thing works in R. So to open the script, it's called AM11 clustering k-means, k-means. That script is in private space, and download it to your computer and drawn up to line 36, let's say. That's the package installation mode. We'll use the facto extra package. This package we used it with principal component analysis, the facto extra package. Okay. And ML Class, which is another package we're using. And ggplot, because facto extra uses ggplot. Let me check that all of this because I ran out of battery in my computer and I forgot to bring the charger today. Library ML Class, library Class. Okay, we ran all the libraries. Okay, now we're gonna. This is optional. This is just I don't like the gray charts in ggplot, and let me know if you're ready. If you're at line 37 already.
Yeah.
Yeah. Okay. Now we're going to generate data from a bivariate distribution, two bivariate normal distributions. So I'm gonna set the seed, and I'm gonna generate a data frame of normal random numbers, 2 columns, okay? And then this is generating random number numbers from with mean 0 and variance 1. And I'll just add to the first column, I'll add 3 because I want the first normal to have a mean 3. And the second column I'm going to subtract 4 so that I have a normal with mean. So the first group would be normal will mean 3, standard deviation 1, and this one will be a normal with mean -4, standard deviation 1. Okay? I'm going to call the variables x1 and x2. So those are my 2 variables, x1 and x2. And I'm going to chart them now. I'm going to do a histogram of both populations. Here, I'm simulating data, so I know there's 2 groups. Okay. This is a histogram of both groups. As you can see, one is centered around the 3 in theory, and the other one should be, this is x2, this is x1, x2, and that's this one is shifted to the left. This one is shifted to the right. We're going to do now a plot of both variables. This is the data that we have. We know if they come from 2 populations. This is one normal. This is a normal with mean -4, and this is a normal with mean -3. Okay. So those are 2 distributions. Now, there's no labels here because this data I just have observation on the predictors on the variables x1 and x2. I don't have a class here. Now, let's do the k-means algorithm. K-means algorithm, we're working with the Euclidean distance, so units are important. In this case, we don't have to standardize them because we generate from the standard deviation 1, just the difference in mean, it doesn't matter. But in general, we need to scale them. Okay? In general, we would need to scale the variables. So if I look at the summary, we'll see that there's no need to scale them because my x1, x2, those are the minimum, the maximum, and the mean. No need to scale them. But in general, we'll always scale them because we need to make sure that the scales are similar. Now everything is around 0 and have a minimum between -2 and 2%. Now we do the k-means clustering, and where fixed k equals to 2. I'm going to use this algorithm here, k-means, with x equals to 2. If I say k-means with k is equal to 2, if I look at the structure of km.out, it tells me that it's a list that has clusters, the centers for each of the clusters, the total sum of squares, the within sum of squares, the total within sum of squares, the between sum of squares, that's between clusters, the size, so I have 25 data points in each, the number of iterations, and I fall down, I don't remember what that is. So I have all the information there. Now, the assignment to each of the clusters is in the variable km.out. Okay? If I look at head of km.out cluster, it's assigned the first 25 to cluster 1, and then from the 36th on to the cluster, I'm sorry, it's 25 to cluster 1, and then it assigned to cluster 2 the other observations. Okay? So I said that k was equal to 2. So I can now plot them And I know the class that it's assigned to, the cluster that it's being assigned, that each observation is being assigned to. So I'm going to plot the, I'm going to use the color, I'm sorry, k-means, k-star, voila, case equal to 2, start to choose different colors. I didn't put the colors here. You can change the colors by saying to use colors red and blue or whatever. It uses two default colors here. So these are the two clusters that it found. Okay, these are the two clusters that it found with this algorithm. Now this is a simple case. You generated the data, and these are from two normal distributions, same variance, and so on. Now I'm going to do it with three clusters. So I run KM out. Now I'm going to call it with three k-means with three clusters, and I do the same thing. I plot it, and now I have nice three clusters like this. Okay, that's the way it's assigned the clusters to the observations to the three clusters that I defined. But I need to specify k. I needed to specify k. Now we said that every time I choose a different, since every time I assign the observation at random, I need to repeat the process several times. Now to repeat the process several times, we're going to use this argument, which is called n star. N star is, if n star is greater than 1, the algorithm will use multiple assignments, random assignments, as step 1, and will report the best results. Okay? Now, and I will compare now n star equal to 1 with n star equal to 20. So I'm going to set seed again, and I'm going to do it with three clusters and n star equal 1. And I'm going to look at the within some squares, and I get 20.05. Then I'm going to set another seed, and I'm going to do n star equal 1. And now those some squares very close, 0.05 to 26. I'm going to do it with n star equal 50. And now I get 26.63, 862. So now my within some squares increase with 50 values of the same. However, we need to do it several times. Now, this is the recommendation: use n star large, between 20 and 50, at least 20. Should use at least 20 as an n star, because we want to do at least 20 assignments of the witness of clusters. Okay? Now, we're going to use this data to use the elbow method, and to use also the three methods we saw: the elbow method, the silhouette, and the methods is the elbow, silhouette, and I forgot the name of the other one. Let's see here. Simon is doing his work. We'll use the factor extra package, which we used for principal components analysis. FBs, I don't know if you remember, I'm sure you don't, because a long time we saw this thing. FVIZ is a function to visualize results for PCA and also for clustering. Okay? Here we'll use FBs for visualizing the results, and the function is with MB clause instead of the function that we use for principal component analysis. So we'll call it PL1. And I specify the method. I'm going to say here within some squares. I will use in the, I'm changing the title, optimum number of clusters, and subtitle elbow method. And I'll do I haven't translated the scripts. I didn't have a chance to translate all the scripts. And this is just to justify the title. That's a chart. So if you look at this thing, the elbow method tells us that there should be two clusters, right? Which is, in fact, we generate from two different populations. We should have two clusters. That's the elbow method. I'm just going to add the line in the second cluster. That's it. I added the line. This function doesn't add the line automatically. The other two will receive, they will add the line automatically. Okay? Although one of them is wrong. Let's go now at the silhouette method. And we're going to use method. What changes here is the method. The first, the elbow method is the width sum squares. The silhouette method, we call it the silhouette as in the function. And we're going to do exactly the same thing with the silhouette method. And it generates the plot. And it again tells us that the right number of clusters is 2. Okay? The right number of clusters is 2. And now we're going to do the gap method. For the gap method, all I changed in this function is the gap method, is the method, which is, I'm going to call it gap. The name of the method in this function is gap underscore stack, because the gap statistic. Do the same thing. The only thing that changes, and there's another parameter here input, which is that. And let's look at the chart. And this is one we have in the presentation. This falls outside the next interval. So we'll choose 2. Okay, we'll choose 2 as the right number of clusters. Okay. Let's do the same with the iris data. We know that in the iris data we have 3 clusters, right? Because we have the 3 species. Turgenica, versicolor, and setosa. So I'm going to use the iris data. And let's determine the right number of clusters by the elbow method. So I use the method equal to WSS. And again, here, if I just get followed by this thing, it looks like there should be 2 clusters. We know there are 3, okay? But the elbow method there tells me that there's 2 clusters. We know that iris data has 3 clusters, 3 classes of iris flowers. So these methods are not perfect, tells me that it's 2. Now, let's look at the other methods. Let's look at the silhouette method. It also gives me 2. It also gives me 2 here, okay? As the right number of clusters. Although we know it's 3. And the last method is the gap stack. That takes a little bit longer. And now it tells me this chart is wrong, because if you look at this thing, this is the right number of clusters is 3, according to this method. It's pointing at 6, but it's not 6 because this observation part is within this interval. Actually, this observation is not in the next interval. This observation, this gap statistic, is not within the next interval. So the right number is 3. Okay, this would be the right number of clusters. K equals to 3. So watch out with this, the chart that generates the function for the gap statistic, because it sometimes comes wrong. So it's better just to use you know that all you have to do is look at the gap statistic and see if it belongs in the confidence interval, the 1 standard deviation interval for the next value of K. And if it doesn't, then you're going to start at the largest value of K, where this one doesn't belong to the next interval. Okay? This one, for example, this one is in this interval, no problem. So that will be the right number. k is equal to 3 according to this method. So in this case, only one method gave us the right number of clusters. So that's why this is called unsupervised learning. We don't know, so we need to go with the tools we have. We'll look at the hierarchical method of clustering also, but, which is another method we can use to complement the k-means method. Okay, so I'm gonna go back to the presentation. We'll talk about the hierarchical method, and we'll do an example with the hierarchical method, and then you'll do an exercise. Okay. Hierarchical clustering is an alternative that does not require to have k specified beforehand. It has another advantage, in that it results in a graphical representation of that's called the dendrogram, which is like a tree. It looks like a tree. It's called the dendrogram. It's a useful thing if we have a reasonable number of observations. If we have millions, it's completely unreadable. We cannot read the dendrogram if we have a million observations. Well, there's several methods to build the dendrogram, but we'll use the most common one, which is the bottom-up grouping. Okay, that's the most common hierarchical clustering. There are several hierarchical clustering methods. We'll only look at one, which is the bottom-up. And we're going to use data simulated from 3 different classes that consist of 45 observations with 2-dimensional data. So this is the generated data. We have essentially 3 groups. That's one group. That's one cluster. One cluster. One cluster. We generate the data, so we know there are 3 clusters. Okay. Now the way the method works is in the bottom of the chart is each of the data points that we have. So we have in each of the 45 data points from class 1 and from class 2 and class 3 are here. So the bottom is the bottom of the dendrogram has all the individual observations. So that's why I tell you, if we have a million observations, there's no way that it's going to be useful to display this thing. Then the bottom leaf, we can call it this a leaf, it looks like a tree, represents one of the 45 observations. Okay? If you count all these things, you'll have the 45 data points that we have generated. As we move from the bottom up, as we move up in the dendrogram, then we'll start seeing, for example, let's look at this one here. As we move up, we see that these 2 observations get joined together. Okay? These 2 observations get joined together. There's a fusion there of those 2 observations. There's another, if we go even further away, these 2 are joined, and so on. So as we keep moving up, we start joining observations. And so at the beginning, each observation is a cluster. Then we move up, and the first point where we join 2 observations, that now becomes a cluster. So these 2 now become a cluster. Each of these pairs of observations become a cluster. And then we keep moving, joining branches, and until we end up with one single tree. Okay, we end up with one single cluster. which is all the data. That's how we continue. The sooner we join, the sooner a fusion here occurs, the more similarity between the two observations is. For example, these two observations, let me erase this part that I did here, just to illustrate this thing. These two observations, these two, are closer than these two observations. So the farther away that I am from the bottom of the endogram, the more different observations are. Okay? So that's how the joints occur, how the two leaves join into a branch, and then two branches join into three branches and so on. And each one of those becomes clusters. So we have, here I have 45 clusters. Then once, this is the first one, right? This is the first, oh no, the first one occurs here. Once I'm here, I have 44 clusters, okay? I start moving, and once I'm here, I have 44 clusters, because I joined two observations, and that were two clusters, now it's one cluster, and so on. And observations that are joined together, that's what I said, but are joined together later, at a later stage, as we start moving from bottom up, they are more different. The similarity is larger. Now, for each pair, I usually there. For each pair of observations, we observe the point where the branches that contain them are joined together. The height of this represents the similarity of these observations. For example, let me erase again this thing. These marks, erase this. If I look at these two, this cluster, and look at, let's say, let me go to, I have another cluster with three. This cluster has three observations, right? It has 1, 2, 3 observations. This cluster has 3. Let me pick one, this one. This one has 3 observations. Okay? Well, these are more dissimilar than this ones here, because the difference in height is larger. So the difference in height tells us how different they are. Okay. Now, we're going to use a pentagram to define how many clusters we have. If we were to decide that there's 2 clusters, we would be splitting the data here. We have 2 clusters. This would give us 3 clusters, right? This would give us 3 clusters. This is 1 cluster. Okay. Now here, the advantage of this thing is that graphically we can see which seems to be the right number of clusters. So if you look at this chart, look at the distance that we have from here to here, and the distance that we have from here to here. This distance is much larger. Okay? So I would place my clusters, I would split my clusters here, because I could do it out here. I don't know what I did here. Essentially, I'm going to take these 3 joint points as the clusters. Okay? The line is drawn here, but because it's I cannot draw now. No, sorry. Because if I move from here to here, from 3 to 2 clusters, I don't get that much separation. So I would go with 3 clusters here. So he tells me that K is equal to 3. K is equal to 3. Definitely not greater than 3, because if you go here, for example, let's pick any other number. Let's pick this one here. If I pick that one, I would have 1, 2, 3, 4, 5 clusters. But there's a lot of, the distances that I see here are very small. Look at this distance and look at this distance. They are very small distances. So that tells me that not that different. So I want clusters to be as different as possible between the different clusters. Now let's see how it works. I'm going to erase some of the slides. Update. Oops. Trying to find the update here because I cannot erase these things. Okay. Now, so the first step, that's also true in other algorithms. First step is always to find how we're going to measure similarity or dissimilarity. Then we're going to start at the lower spine port of the dendrogram. We have each of the observations is a cluster. Each of the observations is a cluster. Then the two most similar clusters are joined together. We look at the most similar, and those are joined together. So we have n-1 clusters. In the next step, we look at the two most similar clusters, and they're joined together, forming a new cluster, so there are now n-2 clusters. And so on. Okay? So it continues until we only have one cluster, which has all the observations. Look at this chart here. We start with these observations 1, 2, 3, 4, and so on. If we use Euclidean distance, we start looking at which are the closest two observations. Well, the closest would be between 6 and 1 and 5 and 7, but it looks like 5 and 7 are closest. So these are these observations are closest. Okay? So I form a cluster there. And now I had, originally I had 9 clusters, now I have 8 clusters. Once I have this as a cluster, I have 8 clusters. Then, on the next stage, I'm going to look at the next observations, next pair of observations that are, or clusters, that are very close together. Okay, now so I start looking at going on the different pairs, differences or distances in the observations, and then I see that these two are very close, 6, 1. Okay, they are very close. Actually, in the first stage, we were decided as to whether it should be 1, 6 or 7, 5, the one that were closest. Now, the next two that are very close are 6 and 1. So I form another cluster there. Okay, so now I have 7 clusters. Here I have 7 clusters. Okay. Now I start looking at which observations are closest. And I see, for example, here that number 8 is closer to 7 and 5 than 2 to 6 and 1. Look at the distance between 2 and 6. That's very large. And 2 and 3, and 2 and 4, and 2 and 9. And 8 and 9, 8 and 2, 8 and 4. So 8 is closest to 5 and 7, which already form a cluster. So now I have 6 clusters. And I keep going like that until I get a single cluster, which is all the data. Okay? This again. So this is the same procedure, but I just shadowed here so to see how this thing is moving up. Okay? As you can see, I started moving up, and first I joined, the first two I joined together were 1 and 6, or 5 and 7, I forgot. And no, 5 and 7, right? Then I keep moving up, and the next ones were 1 and 6. If you keep moving up this line, because remember the vertical distance measures the difference or the dissimilarity. So as I start moving up, I get this. I just put the same sequence we saw earlier, but I'm just putting it shadow here. I move up, and then the next thing I joined with which is 8 with 5 and 7, right? It's 8 with 5 and 7. Because of the distances, if you look at this line here, this is we're measuring dissimilarity. This is less dissimilar than the next point, which is this 2. So that's the same process. People continue like this, and that with the last, the previous to last step, and that the last step I have one single cluster. Okay? So that's how the algorithm works. I just keep moving up, building clusters. Now this is the picture of the dendrogram that we had in the previous slide without the shadow region here. And this is down here I just put the explanation of how the clusters were formed, which is what we just did now. Now, to be able to move up, we need to find the measure of the similarity, which in this case we're using Euclidean distance. Now, let me go back a little bit here and to this chart. Once I'm here, okay. Once I'm here, let's look at this chart here. How do I measure similarity or dissimilarity between this observation and something that has 2 observations? And this observation is something that has 2 observations. So that will determine how the clusters are built. I could say, well, if I'm going to measure the distance between this observation and each of the 2 observations. So that's one alternative. I'm going to measure the distance between 8 and 7 and 8 and 5. And I'm going to measure the distance between 2 and 1 and 2 and 6. Okay? And I'm going to look at which is the smallest of those differences and I join that observation to that cluster. Or I could say I will average these 2 and I will compute the average of these 2. That my average is here. And I will take the average of these 2. My average is here. And I will measure 8 versus the average and 2 versus the average. And then the next cluster I will form will be the one that has the minimum distance between the observation and the average of the observations in the cluster. So I need to define which function I'm going to use to assign a new observation to a cluster that already has more than one observation. That's what's called the linkage function. So if I use the average, that's one thing, that's one type of function I'm going to use. Or if I use the minimal distance between each pair of points, that's another way of doing it. And we're going to find that as the linkage. And there is 4 types of linkage functions that we're going to use. The complete linkage, the minimum linkage, the average, and the centroid linkage. This is the definition of the complete linkage. Complete linkage, we use the maximum difference between clusters. That is, we calculate all distances between the observations in both clusters A and B. Okay, if I go back to my picture, I would say, with the complete linkage, I would measure the maximum difference between clusters A and B. Cluster A had 2 observations, and cluster B had 1 observation. So I would compute the distances and look at the maximum and determine the largest one. Okay, the largest distance. The minimum linkage is the minimum difference between clusters. We calculate all differences between pairs of observations in 2 clusters and determine the smallest one. The average linkage will take the mean difference between clusters. That is, we calculate all the difference between, all pairwise differences between the clusters A and B and determine the average of those pairwise differences. And the centroid is the difference between cluster A centroid and cluster B centroid. That will be the 4 linkage functions that are commonly used. They give different results. In general, the complete and the average linkages are usually preferred because they generate dendrograms which are more balanced. So the 2 preferred methods are the complete linkage and the average linkage, because they provide more balanced dendrograms. This is the algorithm. Essentially, we sort of talk it through. We start with each n observations, with n observations, and the difference between all pairs of observations. N choose 2, all those differences. And we treat each observation as a cluster. Then, for I equals to n, from n to n minus 1, n minus 2, up to 2, and so on. We examine the difference between the I clusters and identify the 2 clusters that are less different and join these 2 clusters and then keep going like that. Okay, the difference between these 2 clusters is the height. So the difference is the height in the dendrogram where the fusion needs to be placed. When we join the 2 clusters, that height is the measure of the difference. And then we calculate new differences among the I-1 different remaining clusters. And that's it until we finish going to 1 single cluster. Okay? The calculated differences in the second step that we saw just now depend on the type of linkage. So we need to define the type of linkage we're going to use. And this is an example of how things look. This is the average linkage. And this is a complete linkage, which are the most common ones. This is a single linkage. Single linkage we try to avoid it because it gives very, very noisy dendrograms. It's very confusing. The dendrograms will take the single linkage. That's why we either use the average or the complete linkage in general. Okay. Now, there are some cases, which we will not cover in this class, where similarity is better measured by something different. For example, if we're trying to group together transactional behavior between different customers in a bank, then instead of using this type of similarity measures, we try to look at profiles, as the transactional profile per customer. So we're looking at, for example, you can think of this as the behavior, transactional behavior of customers. And we will use these profiles to group That's a method that's used in time series analysis to group time series. Okay. Use a similarity based on behavioral pattern. There are some practical considerations that we need to have. One is the variables should be standardized, yes. In hierarchical clustering, it is also important because it's also based on, if we're using Euclidean distance, we need to standardize, okay? Which dissimilarity measure should be used? I would recommend using either the complete or the average linkage, using probably both, and compare it to dendrograms. Which type of linkage we saw, I just mentioned that. And where should we take the cut in the dendrogram to define the number of clusters? It depends on the height. Okay? What we want to do is have clusters that are different enough. Okay, they're as different as possible without having too many clusters. Okay? In K-means, should variables be standardized? Yes. And how many clusters should we consider? And we saw 3 methods to determine how many clusters we should consider. I mentioned this thing earlier. There are ways to assign p-values to a cluster to assess whether the cluster actually exists or is essentially due to noise. We will not cover those. Outliers can have a significant impact. Outliers can have a significant impact in how a cluster is formed. And it may be that outlier is a cluster in itself, in its own. Because if we have first of all, with outliers, the first thing we have to do is try to find out if there's a reason for that outlier. And if there's a reason, maybe that reason is going to tell us that that's a completely different cluster. So that's a different segment of the population, for example. And so the methods are very sensitive to outliers. And one of the solutions that has been used to get away with outliers is something that's called mixture models. But those are known. The methods we saw now are non-parametric. We don't make any assumption about the distributions that generate the possible populations, right? The possible groups. And in mixture models, they're based on mixture of distributions. So they're essentially parametric, and they can be viewed as a soft version of k-means. But they are essentially parametric, and they will depend also on the distribution that you use to build a mixture. Clustering methods are not robust against data perturbations. If I have different sample, I'll get completely different results. Okay? So they are very sensitive. That's why we normally do something. Remember, in classification we use cross validation to be able to select hyperparameters. We can view the number of clusters as a hyperparameter, and we can use bootstrapping. We will not cover this here, but we can use bootstrapping to generate several samples from the same population that we are observing, and to try to define what is the right number of clusters. And given the sensitivity of the algorithms and the type of similarity measure, it's very important to define which type of similarity measure. And again, there are methods where we can use resampling, algorithms like bootstrapping or cross-validation to try to essentially repeat the clustering algorithm several times, but controlling the hyperparameters, which would be the number of clusters, which would be the linkage function that we use if it's a hierarchical clustering, and so on. Actually, there is in the master's program, we do one quarter, one course on non-supervised learning and one in supervised learning. because there are many methods that we cannot cover here in this class. Okay. So let's look at the R script now. I'm going to use now the script for hierarchical clustering. I'm going to use this one because I think that the version may be different from the one that I have in my USB. Oh no, it's this one. It's AM11. That's fine. AM11 clustering method of hierarchical. Which is the different. Let me use AM12. I think that's a newer version. Download it. Not really ours. Is it still running here? Okay. Let's go over this script so that we have an exercise with hierarchical clustering. Again, we're going to use, well, the package ISLR, we already installed it, we installed Vector Extra. Let's generate the data. This is the same data generation, except that the means here are going to be different. No, it's the same means. Okay, and exactly the same thing. And the histograms, we already did the histograms. Okay, and we're going to use the same data with the methods, with the hierarchical method, with complete minimum and average linkage. Okay, to do the complete linkage, we use HC, we're going to call it HC complete, and the function is hclust. We just specify the method, because it's going to change in this function is the method, whether it's a complete, the average, or the single. See? So I'm going to do the complete hierarchical clustering, the average, and the single. Okay? We compute the three. Now I'm going to do the dendrograms, and I'll grab the dendrograms with the function plot. The function plot identifies that HC complete is the result of a clustering, a hierarchical clustering function with a complete method, and so on. So I'm going to do it. To plot them is just the plot function. That's a complete linkage. Oh, I didn't do the problem of this thing. The problem seems to make the three plots together. So if we can look at the three clustering algorithms here, you can see that the single linkage is very unclear how many clusters should we have. Right? It's very clear. It's not clear at all. The complete linkage and the average linkage are a lot more clear in that sense. In both cases, we can see that the right number of clusters is going to be 2. Right? Because, and again, we just focus on these vertical distances. If you look at the vertical distance, for example, if I split here, if I were to split here, if I look at the vertical distance between this and this, and this, that's much smaller than this distance. A lot smaller. Okay? So the right thing to do would be to take 2 clusters. So I can do the split here. It will be 2 clusters. Okay. With the average linkage, I get the same thing, because if I want to put it here, let's suppose that I want to go here and say it's going to be 3 clusters. I will have 1 cluster with only one observation. So that doesn't make much sense, and this distance is very small. So we again here from this we get that k is equal to 2. And from here we get that k is equal to 2. And here k is whatever, because this is very noisy dendrogram. It's a very noisy dendrogram. So we normally base our decision on either the complete or the average or both. Now, to determine the labels for each cluster, we just use the function cut3. And since we saw that the right number of clusters is 2, I'll say cut3 for the complete linkage, cut3, 2 clusters, also for the average and so on. And now I have the labels. See, what I get with this thing are the labels for the assignments of each observation to a cluster. Okay. Look for the minimum, the more reasonable answer would be when k is equal to 4, but again, k is equal to 4 is, look at 1, 2, 3, 4. That's still not good, right? That single linkage generally gives very bad results. So don't worry about it. Now let's standardize the variables. In this case, it was not necessary because we generate the data, but let's scale them first and then do the plot of the clustering, distributions, and main title here. Oh, I forgot to, let me change my plots to bar and row equal C 1,1. Forget to change that. So I just put the labels in the cluster. Okay, with this function, with the plot command, once I have the labels, okay, I can put the labels here, so I know which observation is each one of these at the bottom of the diagram, which are the actual observations there. Okay, and I'll end up with 2 clusters. We will not, don't worry about this thing, because we will not be doing a correlation-based clustering. Okay? To do that, we need to do more applications and more theory. It's trying to understand exactly how that is done. Okay? No, we will see that. We'll stop here. So, because that'll be another topic to include in the exam, and I don't want to do that. Okay? So that's it. As you can see, the functions are very easy to use, and the key thing is for you to identify which is the right number of clusters. And that's it. In clustering. Now, what I'm going to ask you to do is take the data. Let me see if I put it here in the presentation. Now I need to do this right here. Do the clustering with there's a wolf's data. There's a data set which is called, let's see, it's an Excel file. Where is it? Excel with next. Okay, it says moves data clustering. Okay, that data has. Let me run this first part of the script. Please try to do it without running the script. Try to write your own script based on what we saw here. Try to run your own script. Okay. We'll run it. And these are the variables. These are measurements on physical characteristics of some wolves in some place in the world, okay? In North America. And we know for this case, we know how many types of wolves there are, okay? So ignore the last column, which is the subject, because subject has, I believe there's 3 different types of wolves. But ignore that, and try to determine what's the right number of clusters for this data set. The data set is in bright space. See, bright space here. In fact, let me hide this. Let me hide the. Oh, you don't have a script. That's good. Okay, I'm glad you don't have it. I thought I had put it here. Fortunately, it's not here. The wolf script and the data should be here. So let me see if it's not there. We can upload it now. Okay. Whose data clustering? Okay, those are the variables, and these are this is the description. X1 is the palatal length, X2 is the post-palatal length, whatever that those things are. Okay? These are anatomical measures of these groups. Okay, and we have information about these 25 groups, and fortunately also you don't have the group the type of group here in this data set. So do the analysis. I'll split you groups and we'll work 15 more minutes here. We need to leave the room 15 minutes earlier, so the next class can prepare this, and the next teacher can prepare the class, the classroom, and work on this thing. I'll split you. Let me sign out from here so that I get assigned to a group. Okay. Okay. Entonces déjenme ponerlos. I'm going to stop sharing. I'm going to stop recording.